Hello and welcome to lesson 1-4. This lesson is titled Avoiding an Empty Wallet. It can be found on page 47 of your textbook if you're following along. And we're going to be building on what we just did in lesson 1-3, where we're going to talk about exponents and order of operations. So building on that investing money type idea. If you've looked through this, you probably noticed that this one starts with the group work, which is a little unusual. So you will come back and do that when you get into your groups. We are going to jump ahead to page 50, which is where the group work or the classwork actually starts. So at the top of page 50, there's a purple box that they actually want us to fill in. And I'm going to do that one with you just because I think some of these things are important to reiterate. You will learn about two different accounts when you get into the group work. You're going to learn about simple interest and compound interest. Simple interest is known as linear growth, and the word literally means what it says. If you were to graph it, it's a line. We'll do graphing later this semester, but it means it graphs a line. Exponential growth grows faster. It is a curve. It's much hard to do with my hand, but kind of like that. It grows very quickly. In account one, the linear growth or the simple interest investment, grows by adding the same number. We'll do a plus sign for adding. And in compound interest or exponential growth, it grows by multiplying by the same number, which is why it grows faster. Multiplying by the same number gets bigger quicker. Towards the middle of this page, we start with the classwork. Number 1 says, here is a key observation about the repeated multiplication that occurs when finding the value of account 2, that's the compound interest, with an initial investment of $1,000 and 5% compound interest. The value of that account can be found by doing 1,000 times 1.05 raised to the 7th power. So part number 1, we have to explain what we're using here. Rather than writing repeated multiplication, we can use an exponent. In the example right below that, the exponent is the 7. You may have also heard this called a power. We can use those pretty interchangeably. It might be helpful to review something that you'll be seeing again in the group work. You're actually going to come up with the general equations for both compound and simple interest. Since we're dealing with compound interest here, let's talk about what that equation looks like. It is called A, the amount, equals the P, the principal amount you invested, times some growth factor. It's going to be 1 point something. Like in this example, we had 1.05. You're getting that from doing 1 plus the interest rate, and then the whole thing is raised to the t power. In the example we're given over here, it's 1,000 times 1.05 raised to the 7th power because it's 7 years. Now, number 2 says, without using a calculator, write that expression without any exponents. They don't want us to get the answer. Don't do the calculation, just write it out. And you'll see real quickly why we would prefer to use exponents instead of doing it like this. I would be starting with $1,000, and then I'm going to multiply that by 1.05. And the important question is, how many times do I need to multiply it by 1.05? As many times as the exponent is. This exponent was 7, so I have to write out 1.05 7 times. There's 3, 4, 5, 6, and 7. Yeah, I almost fit it in. I tend to write too big. And then 3, they want you to calculate it. They want to say, okay, let's find that answer. So I can take some minutes for the calculator to turn on. I don't know why. It's been behaving better today, but There we go. I can type in 1,000 times 1.05, and my lovely touchscreen calculator, forgot the times button, times 1.05 times 1.05. I'm going to keep track of my hands, how many times I've done that. That's 3 times 1.05 times 1.05 times 1.05 times 1.05. So that should be 7 times. And I get an answer of 1,407 and 10 cents. So we did it the long way, but we got there. $1,407.10. Now, it would be a lot easier to use the calculator doing the exponents and just putting a whole formula in. So our formula was 1,000. And then in parentheses, we had that growth factor. In this case, the growth factor was 1.05. End your parentheses. Now, here's a new function on the calculator to learn. The caret button allows you to type in any type of exponent. The caret button on the graphing calculator is right below the clear button and right above the division button. It looks like a triangle missing its bottom half, bottom leg. So I push that button and a little box appears. Now I can type in what power I want. In this case, it was 7, and then I can hit enter, and it gives me the same answer. So again, given that mathematicians are notoriously lazy, we're going to do it that way probably more often than not. All right. The bottom of this page, bottom of page 50, so number 4 says, in account 1, where the simple interest, let's try that again. In account 1, where the interest is simple, so not compound now, the account value goes up by $50 each year. That's 0.05 times 1,000. Write a calculation that would find the value after 7 years and then find it. So it's not our exponent formula this time. This time we're starting with $1,000 and we're adding $50 per year for 7 years. So that's the calculation. Now we can just do it in our calculator to get the answer. We do 1,000 plus 50 times 7. You can also use the parentheses if you like. And I get $1,350. So you see it does grow at a much slower rate. The compound interest one with the same interest rate, the same amount of time, is significantly more. Top of page 51. So we're going to try to summarize this now. Let's put this all together and summarize what we've learned. With linear growth, the value after a certain time is calculated using a starting value plus some constant times however long I'm investing for, some amount of years or time periods. Compound interest, or exponential growth, we take the starting value times a growth factor. Again, that growth factor is usually going to be 1 point something, depending on what your interest rate is. Raised, and that growth factor then will be raised to a power. And that's why it grows so quickly. Number 7 says, without trying to give away the answer to number 6 too much, part of it involves a power. What is the significance of the exponent? Let's look back at what we did in numbers 1, 2, and 3. The exponent was 7. What did that 7 mean? It meant 7 years. So our exponent is going to be the number of time periods. Most of what we will do in this class, if not all, will be yearly. But as you move on to other classes, you may learn about compounding quarterly, compounding monthly, that kind of stuff. So you are counting time periods. It's a more general definition. Purple box, middle of page 51, means there's something important here. The purple box talks about how to calculate the values for both linear and exponential growth. When a quantity increases based on linear growth, the value after a certain number of time periods can be calculated using this. The new value equals the original plus the amount of growth per time period times the number of time periods. So that's, I think we did that in red before. I don't remember what color we did, but that's okay. That is our linear. Also our simple interest. This one is our exponential or our compound interest. We take the original value times some growth factor to raise to a power. They have a nice solved example for us here. They work through it. They show how to work through it. So let's see what's happening here. Just make sure you hit the highlights of this. Muhammad invested $25,000. Each year, it's earning 3% of the current year's account. Each year, 3% of the current year's account is earned in interest. This is compound interest. So compound interest, we're earning interest on the interest, which is why it grows so quickly. So the first question, I really like this one. It asks us what the growth factor will be, because that's a pretty important question. And they give it to you down here. So it's the 1 plus the interest rate. This interest rate was 3%. Written as a decimal is 0.03, so 1.03. What will be the total value of the account after 7 years? Well, they did that formula we've talked about. The initial amount invested, 25,000 times the growth factor raised to the 7th power. And then they say, what would have happened if this had been simple interest? Well, I have to first do 0.03 times 25,000 to figure out how much I'm making each year. And then I multiply that by 7 and add that to the initial amount. So again, you can see the compound does grow much faster. Page 52. It says, use what you've learned about linear and exponential growth to calculate the value in each of the accounts we've been studying. Make sure you write out the calculations you did. So account 1 was simple interest. It was the simple interest. And you'll see more of this in the group work. So we're kind of getting you ready for the group work, and the group work should come fairly easy. We invested $1,000. And then we have to figure out how much I'm earning each year. So I take 1,000 times, it was 5%, so 0.05, and then times 20, because it's 20 years. So let's go ahead and put that into our calculator and calculate it. Let's clear this. So we're going to take 1,000 plus 1,000 times 0.05 times 20 years. After 20 years, there will be $2,000 in that account. Apologize, that 1 0 looks a little bit like a 6. We'll fix it. Let's now do account 2. Account 2 was the compound interest. For the compound interest, we were investing $1,000 again. It was still at 5% interest, but because it's compound now, I have to turn that into a growth factor. So I take the 1 plus 0.05 and I get 1.05. My growth factor is 1.05. If it was 3%, it would be 1.03. 12%, it would be 1.12. And then I raise it to the power of the number of years, which is 20 in this case. And then we can put that into my calculator. 1,000 parentheses 1.05. That's my growth factor. Remember, the caret button is below the clear, above the division. Looks like a triangle missing its bottom. And I want to put that in for 20 years, and then I hit enter, and it tells me that there is $2,653.30 when we round that the right way. So 2,653.30. Orange box is good practice if you decide you want to do it. Below the orange box, it says, we've used interest to help you practice on expressions that combine more than one operation, but there's a lot of other situations that lead to calculations of this type. Here are some examples just to kind of work on what we've learned in here without focusing on interest. In her final 2 days of preparation for a triathlon, Amal hopes to swim, run, and bike a total of 50 miles. So I know I'm going to need that at some point. She works out at a nearby state park with a swimming quarry and running biking trail. 1 lap in the quarry is 0.25 miles, so that's her swimming. The trail, which is her running and biking, is 3.3 miles. The first day, Amal swims 6 laps, runs the trail twice, and bikes it 5 times. How many more miles does she need to cover her second day? So, to give us a template here, it says take the number of swim laps, which I guess I forgot to mark these down too. All that information, sometimes that's the hardest part of a word problem, is pulling out the information. She swam 6 laps, and the swim lap distance was 0.25. She ran the trail twice, and the distance for running was 3.3. And then she biked it 5 times, and that was also 3.3. Fix my plus sign there because I was looking at it thinking it was a 7. So that's the setup. And then number 10 says use the order of operations to calculate her first day distance. So we are going to multiply each of these. I can do them in the calculator all together if I want, or I can do bit by bit. So we know the swimming was 6 times 0.25. So she swam 1.5 miles. So order of operations, that's that PEMDAS. Please excuse my dear Aunt Sally. We do parentheses first, then exponents, then multiplication and division, then addition and subtraction. You'll see a little bit more of that, I believe, when you get into the group work. And then for her running, we're going to do 2 times 3.3, which is 6.6. And then 5 times 3.3 for her biking. 5 times 3.3. So she has 16.5. And then we're going to add all this together to figure out what her first day distance was. So I'm going to add to that 1.5, and I'm also going to add 6.6. So her first day distance was 24.6 miles. You could have typed in the whole expression from number 9 into your calculator. Your calculator does know order of operations and it does it correctly. That's why we use scientific calculators. So then to calculate how many more miles she needs to cover her second day, we look back at the original problem. She wanted a total of 50. So I'm going to take 50 minus 24.6. Again, I might want to do that in my calculator. So 50 minus 24.6. Silly calculator. And if I click on too many times, it goes away. Let's just clear it all out and try again. 50 minus 24.6. She has 25.4 more miles to go on day 2. All right, the last problem. This is the bottom of page 52. It says, according to the McDonald's website, a regular hamburger contains 250 calories, a small Dr. Pepper has 140 calories, and a small order of fries has 220 calories. Write an expression describing the total calories in a dinner consisting of 3 hamburgers, small fry, and 2 small Dr. Peppers. Obviously using all the calories it gave us. So we have 3 hamburgers times 250 calories each, plus 1 small fry, so that's just 220, plus 2 small Dr. Peppers at 140 calories each. You could do this bit by bit, do 3 times 250, 2 times 140, then add all the numbers. But I do want to show you that your calculator will do it all at one time. 3 times 250 plus the 1 small fry, which was 220, plus 2 times the 140 for the drinks. So that meal would consist of 1,250 calories. So now that you've done the classwork for lesson 1-4, you'll go back and work on the group work, and I hope you have an excellent day.